bad. This is gonna be a rocking episode.
How did I press record a second too late? Because if I had pressed it a second earlier, you would have heard Benjamin do the perfect impression of R2-D2 during a space battle.
Oh wow, really? I was just going.
That was
okay.
That was
Have
great.
you seen? Goodness, golly, the Star Wars prequels were absolute garbage. But somebody, the episode one is called The Phantom Menace. But somebody way back when it came out made a edited version of Phantom Edit. Have you seen that?
Okay. Phantom Edit. I don't think so.
The Phantom Edit is great. They basically cut out every single shot where you see or hear Jar Jar or Anakin. So now this whole movie is reduced down to maybe 18, 20 minutes. And there's an actual storyline. You actually follow R2-D2 as he's flying through space, and he's on some spaceship, and people are shooting his fellow astromech droids off of the wing, and he's the only one left. And then he finds his way down to some planet, and he gets into the back of some yellow spaceship and flies out and blows up the people responsible. It's fantastic little 18-minute droid revenge story. It's fantastic. Better than the entire prequel. Better than the entire prequel trilogy, I would say.
Well, I mean, the droids are the heroes of the story. Like, you would not have any progress without constantly being saved by droids. So
or having them translate something for you, or having them clean something for you, or having them plot a course or something. Without them, we're just humans bumbling around through space.
Oh wow. Okay.
We should do an episode of me just ranting about Star Wars.
Well, this is good. No, I would love to do an episode like that. And I was thinking that today's episode should be just rambling, because today's episode, if I'm not mistaken, is our 42nd episode. Is that right?
That's right. Episode number 42.
42! The answer to everything. The universe.
The universe and everything. Again, I'd like to take this opportunity to apologize for the one time I said Hitchhiker's Guide to the Universe. It's Hitchhiker's Guide to the Galaxy. I am fully aware. I was struggling for words. Sorry. Won't do it again. I was warned about it yesterday, as a matter of fact. Welcome to episode 42.
Oh, wow. 42.
The answer to the life, the universe, and everything. And as if I'm not mistaken, I believe that science-minded folk like yourself are actually working towards trying to find an answer to the universe and everything, called the Standard Model. Is that correct, Mr. Scientist Man?
I do appreciate the being lumped into the group of the real scientists by you saying science folk like you, because I find weird things that show up in astronomy, and then I do observations and I do modeling and I do some science to figure out what the weird star is, what the weird thing that went like what is it? What's it doing? Mm-hmm. But the real scientists are these particle physicists who are doing both simulation and theoretical calculations, and then trying to match that to whatever observations we can get that are relevant to, as you said, understand the fundamental parts of the universe, to answer this question. And the answer is, as far as they've found, not 42.
That was beautiful. It is not 42. I really hope there is precisely 42 of something. Just by happenstance, scientists bump into like 42 possible quarks. There's the spin and the charm and the this and the that and whatever, the up and the down. And I hope they actually get to 42 possible quarks, just somewhere down the line in this infinite going down in size of small little pieces of things. Oh, there's only 42 quarks.
I
That'll be
mean,
great.
maybe like it's not at a certain point. Like we might find 42 of something. There
Sure,
could
of course you
be
have to.
42 combinations of quarks and anti-quarks and
Something.
various leptons and gluons and muons and Jimmy neutrons and all these different things.
Oh God! If anybody out there in charge of naming the ooons, please name one a Jimmy Neutron.
Just a Jimmy.
Just give me a Jimmy.
It looks kind of like a neutron, but it's not. What should we call it?
Jimmy.
Jimmy.
The term standard model was first coined in the 1970s by Abraham Pace and Sam Treman. They were theoretical physicists, and they use it to informally describe the unified theory of the strong, weak, and electromagnetic interactions, which are emerging with at the time. But research into coming into understanding the standard model started way before that, like in the 1920s, when Paul Dirac was formulates the Dirac equation, and he predicted the existence of antimatter. From what I read, that is the beginning of our coming to find and starting to understand the standard model.
I think it's you can do this like Carl Sagan type of approach where you can arbitrarily draw the line at the beginning as far back as you want. In order to make
some guy invented
life,
fire,
you must create the universe.
Came to the standard model. Yeah, sure.
I think the kind of quantum revolution that we were experiencing in the early part of the 20th century definitely like laid the foundation, and a lot of people like Dirac and Pauli, they all focused on this stuff, and it's kind of wild how much we were able to understand just from the math before we had the ability to make any sorts of measurements. I mean, things like the super colliders, right? These underground loops like you have at CERN, where they basically accelerate particles to super duper high speeds and crash them into one another, and then in that interaction, that collision produces all of these different flavors of subatomic particles. And the quantities in which they're produced are what was predicted, right? This is like the perfect example of the scientific method at play. You make a prediction, you test it, and it either confirms or invalidates your prediction and your model. And so the standard model has been increasingly proved correct, despite the fact that there are still some things that like we can't explain just with the standard model.
Right. Actually, that's part of the questions I have for you.
Oh no.
The standard model, like I said, doesn't explain everything. And the three big things that I've read is dark matter, dark energy, and gravity.
Yes.
So the question is, because this is mathematics and science beyond any of my possible understanding, so what work is being done to incorporate those three things into the standard model? Is a standard model basically like this constantly evolving principle, or is it something that it's done now? It incorporates everything except for those three things. We're done. We need to find something new for which the standard model will be a part.
So I would put dark energy on the side for a second. And if we just talk about the gravitational force, right? So as I think I hinted to in a previous episode, the split between the different mapping on the standard model map is kind of like the particles that carry a force and the particles that are affected by a force.
Okay.
Right? So like photons carry the electromagnetic force, and electrically charged particles are affected by it. Right? All particles that have mass are affected by the gravitational force, right? But we don't know, we haven't yet proved that there exists a particle equivalent to the photon that is the thing responsible for mediating the gravitational force, like a hypothetical graviton, I think some people have called it. And so there's like a placeholder for that sort of particle that would be a force carrying particle for gravity within the standard model. We just haven't found it yet. And then I think that once we found such a thing, that could potentially lead us down the road of explaining dark matter, because dark matter, while it doesn't interact with the electroweak force or the electromagnetic force or the strong nuclear force, it does interact with the gravitational force. So finding a graviton type thingy would lead us in the right direction. But there is also like really fascinating research that's being done on what different particles could potentially explain what dark matter is. And there are folks who are using the standard model and different permutations of stuff that exists in the standard model to try to come up with alternative explanations.
We're trying to find... Well,
that was a lot, I know.
That was a lot. And it actually segued into a question I had earlier. I had written down, excuse me. And you said we're trying to discover some of the particles that make up dark matter, but we can't see dark matter. Are we trying to find particles that make up dark matter, and dark matter is something that we can't see yet? Are these particles existing in our matter, that the 25% of the matter universe that we can see and touch?
So
Not a good question. Is that clear?
No, it's a good question. I think. Okay, so as I mentioned, like there are these additional forces besides gravity,
right?
Like the nuclear forces, the electroweak, and the strong force, and there's also the electromagnetic force. So what people are doing in some cases are coming up with hypothetical fundamental particles or elementary particles that would have, let's say, no electric charge and no quantum spin. And these particles would therefore not interact with those other forces. And so by kind of inventing new hypothetical particles, you can see if that particular thing will fit in with the rest of the picture of the standard model and also explain dark matter. So one example of this is axions.
Okay.
So, yeah.
What's an axion?
It's one of these hypothetical particles that has been theorized to like.
Does an axion have a super partner?
Does it have a super partner? I don't know.
I just found that electrons
and Robin.
Fermions and bosons are super partners, and bosons and fermions are super partners. Or rather, electrons and selectrons, and photons and photinos, and quarks and squarks are super partners.
Is this like NASA and SNASA?
I don't know. You're a scientist, dude.
Yeah, but not this sort of science. We do have hopefully a friend and colleague of mine who works on axions and astroparticle physics and dark matter, who will hopefully come on in one of our upcoming episodes and be able to explain this much better than I can. But until then, I'm not super familiar with super partners.
Okay. Excuse me.
You are excused. I excuse you.
Thank you. So.
Yes, you're the back.
Me in the back. Supersymmetry.
Supersymmetry, yes.
Supersymmetry. Um, Stupidly, my favorite thing about supersymmetry is that it's abbreviated to SUSY. Susie. Is it pronounced Susie when people say it in your world? I'm going to the Susie
Again,
conference.
these are particle physicists. I don't go to those conferences. I'm not cool enough or smart enough to go to those conferences.
I'm going to ask one of them one day. Anyway,
You should. Susie or
supersymmetry
Susie?
is something that scientists are working on to further expand upon the standard model, unifying forces, bringing in dark matter and incorporating gravity and these types of things.
Yes.
Yes, and it's in those notes where I found about super partners, which is funny. But other than supersymmetry, what other types of work is being done to, I guess, improve the standard model?
What kind of work is done to improve the standard model?
Well, the standard models, it's not done, and
No,
nobody said, okay, standard model's done, stamp it, next problem.
pack it up, kids. We're going home. There, at least from what I can tell you on like my side of things, in terms of observational astronomy. So one of the things I might have mentioned before that I think is the coolest thing in the world is the fact that there are some astronomical observatories that are deep, deep, deep underground. And those are for neutrino astronomy. So neutrinos are subatomic elementary particles. Specifically, they are leptons, which are a type of fermion. And you have different flavors of neutrinos. You have a muon neutrino, tau neutrino, and electron neutrino that have similar but slightly different properties. And the various flavors of neutrinos we have predicted can only be produced in certain, let's say, in certain physical processes. So like something has to happen in space, like a supernova or a thermonuclear reaction like we have in the sun. And that stuff should produce neutrinos.
Okay.
So the work that's being done, at least that I know of, is to see if we can build these underground laboratories that are isolated from, surface effects, and build these things that can capture the interactions of neutrinos with like it's honestly wild, right? Like neutrinos can pass through the Earth.
Anything. Yep.
Anything, right? They pass through. They have a very, very low interaction cross section, which is basically a fancy way of saying how likely they are to interact with something as they move through it or near it. And so they're basically moving at nearly the speed of light. They have a very low cross section of interaction, so they're basically just zooming through and not hitting anything. And so these detectors that we build underground, like at the Gran Sasso in Italy, which is like inside of a mountain, or Kamiokande in Japan, which is like this giant tub of water, this giant volume of water underground. They have these really complicated indirect ways of seeing, well, if a neutrino hits one of the atoms in here, it would interact in a certain way that would produce a detectable signal indirectly. And then you detect that signal that's detected, and you reverse the direction that it was coming from. And by doing this, we have detected neutrinos coming from the sun. We have figured out exactly what type of neutrinos they are and confirmed the sorts of, I think it's I want to say beryllium interaction. I'm probably diving too deep into like the details, but like it's honestly, it's not something I work with on a day-to-day basis, but it is wild. Like neutrino astronomy or neutrino observations that are indirect and also like accurately measuring, for example, the position of the sun through the Earth, since you can have neutrinos coming from the sun passing through the Earth and hitting these detectors.
something that small, moving that quickly,
Yeah.
having an indirect interaction maybe with something in this giant cavern
Yeah.
that gives enough information to give you a direction that it came from.
Yeah.
God.
It's like really, really wild. I don't remember the exact descriptions of like what materials. I want to say that they were it was like heavy water, like heavy with deuterium, and it was the deuterium that the neutrinos were having an interaction with, and that reaction would produce a detectable particle, and there are detectors on every side of the volume that this heavy water is in.
Right.
So like, if the interaction is this way, coming from the left, and then a particle it produces would come from the right, so you know that the neutrino was coming from the left, etc.
Simple. You can build one at home now. All right, cool. You need a bathtub, and you're done.
Hey Benjamin, are you tired of the same old standard model?
So...
You...
Stop. That was perfect as is. That's it. Please. Yes, I am tired of that same old standard model.
Are you bored of strings that just don't resonate anymore?
Yes.
Introducing quantum flex, the particle physics theory of the future. That's right, now with 50% fewer dimensions but 100% more mind-blowing equations. Sick of explaining why gravity and quantum mechanics can't play nice? With quantum flex, they're BFFs. It's not just a theory, it's a lifestyle. Featuring the new Gluino, it's like the gluon, but you know, spicier. Get ready for particle interaction so smooth, even Einstein would say, whoa, slow down there. Quantum flex, TM. Now available at your local theoretical physics institute. Warning, may cause spontaneous breakthroughs in understanding the universe. Quantum flex, because your universe deserves an upgrade.
That's brilliant. 50% fewer dimensions, 100% more equations. Spicy gluon? You got me. Sold. Where do I sign up?
I'll send you the link.
Please. And for our audience, we'll post the link to this fictional thing. That was fantastic.
I feel like one day I'm just going to be watching late night TV and I'll see an ad for the quantum flex come on and I'll be like, that's the thing.
Operator standing by, little clock ticking down. You have 22 hours left.
This product is both simultaneously sold out and available. Oh man.
12 easy payments.
42 easy payments.
40. Yep.
Yeah, there we go.
This is episode 42.
You know what? You're right.
It is. Let me jot that down.
And
jotted.
Fantastic.
Here's a question for you.
Yes.
Going back to just before our delicious commercial break.
Spicy.
There are the math and the theories that go into the evolution of what has come to become the standard model.
Mm-hmm.
It's been going on for a long time, much longer than there's been actual physical experiments that are built, bathtubs in a mountain to catch or inadvertently detect a neutrino.
Yes.
How did the scientists get from we're doing the math to okay, we've reached a point now, we have to build this contraption? At what point do you get to this place where like we've hit a we've hit a wall of sorts, but if we dig a hole and we line it with this and fill it with
Mhm.
that, we'll be able to take huge steps forward and until we need another whiz bang gizmo. How is that? How do you propose? Who decides to propose that? And I'm sure there are multiple people working on multiple facets of these things. Who gets
Yeah.
is just the best salesman wins, or is the actually have to prove to like some kind of a board somewhere full of money that says, okay, we'll build Kavi's idea, but not Benjamin's, which
Yeah.
would be
I think
really
this
smart,
is
by the way.
I think that this is a really good question for science in general and how science gets done.
Mm-hmm.
And I'm not saying it's the perfect model, but in terms of making progress, it does seem to be producing results, right?
Right.
And and generally the way this works is you have people who get interested in a particular topic in science, and they say, I wonder why this is like that. And they might be spurred on to do that based on something they learnt in a lecture or something that they found in their research when they were, a grad student. And they get this question that's kind of, they think is interesting. And they think that it's also potentially knowable, which is an important thing, right?
Okay.
Because a question might be interesting, but it might not be actually knowable or measurable at all. Which is kind of a bummer, but it is what it is. So what you then do is go through these steps of figuring out, okay, I am going to propose, I'm going to apply for this position as let's say, a junior researcher at an institute that has a place for a junior researcher and say, hey guys, I want to study this thing and I think this thing is interesting. And the institute, the university, the college, whatever, will agree, disagree. And when you're hired for that position, you spend that time doing research to figure out, okay, this interesting question that I had, how would we answer it? Is it answerable? And you start doing the math and you start going down the rabbit hole of figuring out, okay, so these are the equations that describe the situation that I'm looking at. In a case of particle physics and the standard model, you write what's called a Lagrangian, which is kind of an equation that shows you the different components of the energy of a system, in this case made up of fields and interactions within the fields, and that's a whole other thing. And if these equations lead you down the rabbit hole to a point where you say, okay, if I can isolate this part of it and I can isolate that part of it, this is a measurement that I could potentially make that would prove this new thing, that would confirm this particular discovery. And then the next round of either job applications or government funding for research or whatever it might be, that researcher would go and say, hey, here is this giant stack of literature that says why this is an important and relevant question. And here is my novel approach, or an approach that was abandoned decades ago because we didn't have the technology, but now we do. And this is how we're going to solve this issue. This is how we're going to build a thing that will do a measurement, it will do a science, and that will give us a result that will fit into this theory, this bigger picture, and answer this question. And then you start assuming that you get the funding.
Start building.
You start building it, and I think one of the best examples is like you look at gravity, right? And you see we go from Newtonian gravity, 300-400 years ago, where we finally have an equation that describes the motion of things under the influence of the gravity of a massive object. And then it took hundreds of years to get to general relativity, to Einstein's theory that describes how space-time is warped by massive objects. And that's kind of a more evolved and more complex theory of gravity. And at that time, there were certain details that we had no way of testing, right? Because any collision of two massive objects, like two black holes, which weren't even theorized then, that could create a ripple in this space-time that Einstein was predicting. And nobody really thought too deeply about it because, like, we had no way of detecting it anyway. These ripples in space-time were, like, smaller than the size of a proton. And then half a century later, I want to say in the 70s, you had people like Kip Thorne who came up with the idea of building LIGO. Oh, wow. Right? Who came up with the idea of building a detector and saying, we are going to find a way to make this measurement to confirm this theory. And then it took them nearly another half century to actually build the thing, get it online, make the detection, and then a short few years later, Nobel Prize.
It just takes 100 years and change. I didn't know it went back that far. LIGO.
I think the original idea for LIGO was from the 70s or 80s. The idea of building. I think they started building it in 1992, something like that.
Sure.
But the original idea for building an interferometer for gravitational wave detection was from around the 70s, I think. Yeah.
Jeez.
So it's step by step. It's I think, as Newton said it himself best, standing on the shoulders of the giants who came before him. This is what science is, and especially with something like particle physics, which requires so many different, both theoretical and computational, and then engineering to build these detectors efforts over generations. It's step by step.
That's awesome. That's I like how you just whittled this. You simplified the whole how do I build a giant whatever thing. You simplified it so nicely. This makes me feel like I can go out and build a thing real quick. Get interested in something, do some research.
Yeah. Do it.
Wonder. Boom.
Do the thing. Absolutely.
I have one more question. A silly question, hopefully, but a fun one. And
no such thing as silly questions.
Buckle up. For the standard model, is there a beautiful and simple equation for the standard model? Or is there any work towards that? Something like E equals mc squared, or Newton's second law, or Planck's energy frequency relation, or the Pythagorean theorem. Is there any kind of cute little gobbledygook of letters equals letters and numbers that looks good on a t-shirt, but it means like this is why everything works?
Yes, but also no. If you want to Google, I mentioned a moment ago, like writing down the equations that describe the physical situation.
Right.
If you want to Google the Lagrangian for the standard model, so that's Lagrangian. For those just listening, no, immediately no. So there is an equation, but some people would argue that it's beautiful, but it is not simple and it is not little. There is a shorthand way of writing the Lagrangian, but for the most part, it is if you expand out all the terms, it is a massive equation that probably wouldn't fit on a t-shirt, basically describing all of the different energy terms required in the standard model, which is the particles and their interactions and the fields. We barely even talked about fields this episode, but the fields in the world of particle physics are these kind of all important mathematical objects that are defined at every point in space-time. And without the field, like the field is kind of like a factory or an engine that makes a thing happen at a particular point in space-time. So even with no particles, the field is still there, right? So like the Higgs field is the thing that's responsible for giving mass to all other particles. And that field exists everywhere. It surrounds us. It pervades the universe. Exactly. But yeah, so the Lagrangian, that beautiful equation that folks at home are probably just now opening their phone and Googling and throwing their phone out the window in disgust. That Lagrangian includes all the fields and the interactions and the particles and blah, blah, blah.
Incredible. It looks like hieroglyphics.
Well, there is a lot of Greek on there.
There is. There's a lot of Greek on there. Lots of W's, lots of M's.
Yep, W's for the W for the W bosons.
Oh my god. I love it. All right, let me answer the question. To be honest, to be fair.
Yeah.
For a standard model equation that explains the universe, that's pretty concise.
I mean, it's basically 42 lines, right?
Oh.
Write that down, quick. Benjamin is counting the lines. For folks who are just listening, I can see his lips moving as his eyes go down the screen.
I did it really fast. I got to 39. I was really hopeful.
Ooh. Oh, wow. Oh, wow. That's amazing.
I'll do it again. That's fantastic.
Welcome. Yeah.
And you can buy this equation on a T-shirt. The reduced version one that doesn't have all the different fields explained out or whatever. It looks
for the full.
Looks nice on
the full version. There would need to be like a blanket or maybe a scarf, a really long scarf.
Yeah, really long one. I have ideas. This is wonderful.
And for any particle physicists,
I think we covered it good. Yes, go on. Sorry,
we did.
I cut you off.
No, we have covered this well, and I think I'm grateful that I haven't been stumped so far this episode, but I will apologize in advance if there are any particle physicists who are listening who feel like I didn't do justice to their field. See what I did there?
Get it? Because you left out fields. We didn't talk about fields. Double entendre fields.
Yes, a super entendre. And so I do apologize if there was anything that was imprecise. Please shout at us on the internet and shake your fist at us and explain why we were wrong, or do one better and come on the show yourself and put your money where your mouth is and explain why you think, or just do a better job of explaining particle physics than we do. As I mentioned, I'm not a particle physicist. I am a simple radio astronomer.
You're closer to a particle physicist than I am. I can't even pronounce particle physical weapons.
Are you okay? I think, Benjamin, your whole left side.
Work is to not pronounce it. I can't even pronounce birthday cake and laughing. What?
The whole left side of Benjamin's body has now slumped over to one side. I jest. This was good. I think we've gotten a whole lot of material for future episodes.
I think this is going to be a good primer episode for when we do have a particle physicist come on. And then we can tell people go back to listen to episode 42.
Yup.
And then join us for the deep dive.
Oh, yeah. We'll talk about all the deeper things. We'll talk about fields in depth. We'll talk about the role of special relativity in the standard model. We'll talk about symmetries and groups and gauge invariance, which is a whole other thing that I'm glad we didn't talk about.
Theories.
All the theories, lots of theories. And hopefully we will not talk about string theory because nobody should be talking about string theory anymore.
Is that really? It's out. That's out.
Oh, yes, darling, string theory is so last decade. It's not. It's just not happening.
String theories were so 2000s.
Seriously.
Seriously,
Yes.
I don't even talk about string. Oh, look at you
No.
driving around in a string theory.
I know. No string theory. Talk to me about quantum flex. That I want to hear about.
Oh, quantum flex is going to happen. Quantum flex is going on.
Quantum flex. TM. Oh, man. Benjamin, where can the good people find you on the interwebs if they want to learn more about you?
The good people and the not so good people can find me on the interwebs under my moniker of Science Actually. Find me on Facebook, find me on Threads, Instagram, Twitter, Mastodon, Hive, LinkedIn, and of course, if you'd like to listen to more episodes of our show, please go to anywhere you get your podcasts. And if you'd like to see our faces make the sounds that you're hearing, you can check out our TikTok channel and our YouTube channel.
That's
How about you,
right.
Avi?
That is right. If you would like to find me, too bad you will not, because I am hiding. I am hiding on the other side of the planet, where Australia is hidden. But if you would like to see my shenanigans on the interwebs, you can find me at Fun Fact Science in all the places. Hopefully, you will be both listening to this show and also watching it to see the visual shenanigans that Benjamin and I come up with. And I'm looking
really
forward to. They are. I think so. I watch back some of the episodes and I just crack up laughing. But we will both, in our own heartfelt ways, see you and hear you, or you will see us and hear us in the next episode of Science Actually Presents The Nerd and the Scientist.
Bye, everybody.